chemical formulas, and we're going to look at percent composition. The chemical formula actually tells you the number of atoms in each compound. For a molecular compound, it tells you actually how many atoms are in the compound. For example, sucrose is two rings actually of carbon atoms that are joined together, and in solution they maintain that molecular shape. Calcium chloride is an ionic compound, and the formula tells you the ratio. There are 2 chlorine ions for every 1 calcium ion, and in solution they're going to be present as calcium plus 2 ions and 2 chloride minus 1 ions, but they will always be there in a 1:2 ratio. So the important thing about these subscripts is that they represent number of atoms per unit or number of moles of an element per mole of that compound. Now, in the lab, we're dealing with mass, and so we're going to be looking at the relationship between mass and moles in these systems. But what we'll do first is look at percent composition. So, there are 2 ways to deal with percent composition, either from a chemical analysis, where you could have the mass of each compound, and then the percent is equal to the part divided by the total times 100. And you'll also be able to do this from a chemical formula, because if you know the formula of a compound, you can calculate its molar mass, and you know the mass of each element over the total molar mass, and that times 100% will give you a percent composition. So either way. So we're going to look at 2 of these examples, an example in both directions. And this is from page 39 in the back of your textbook. So you can go to that page and follow along while I do this. The first part is from analysis, and this says that you've got compound A, and you have found that there are 250 grams of sulfur in every 600 grams of compound A. Well, that's the part over the total, and then you're going to multiply that times 100%. So, if you took 250 and divided it by 600, you get 0.417. If you multiply that times 100, you get 41.7%. This means that there are 41.7 grams of S in every 100 grams of compound A. Now, both of these relationships tell you the same thing, and also look at 0.417 over 1 also being a ratio, just like 50% is really 0.5 divided by 1. Now, the important thing about this is also that you can use this percentage as a conversion factor, because this will allow you to convert between sulfur and compound A. So, the next question says, if you had an amount of compound and you knew that there were 0.06 grams of sulfur in it, how much compound A is actually there? Well, you know that there are 41.7 grams of sulfur in every 100 grams of compound A. That allows you to cancel the sulfur. This is a mass percent, So the units in that cancel out, and they are mass units. So doing this mathematically, you would have 0.06 times 100, and then divide that by 41.7. And your answer is 0.144 grams of compound A. On the other hand, if you had 30 grams of compound A and you wanted to find out the number of grams of sulfur, you would use the 41.7 over 100, and that would be sulfur over compound A. So here you would have 30 times 41.7, whoops, we don't have all the numbers in, it won't work right. And then divide that by 100. And that gives us 12.5 grams of sulfur. So this is an example of getting a percentage and then using a percentage as a conversion factor. The second example is a hydrate, and the little dot there in the middle is called a water of hydration bond. It is a weak bond. Water is part of the crystal structure of the salt. It gives the salt a unique crystal structure. But it is a fairly weak bond, and a little bit of heat will break it. So we can pull that water off pretty easily, and that's part of what you'll be doing in lab. Well, if you want to get the percent water in the formula calcium sulfate pentahydrate, because there's 5 waters there, you need to first find the formula mass of the compound. So I'm going to take the copper, the sulfur, and the oxygens, 1 copper, 1 sulfur, 4 oxygens in the salt, and then the H's and the O's in water, and I've got 5 waters, so I have 10 H's and 5 O's. Multiply them times their atomic mass, and adding them up, we get 63.5, we get 32, actually this should be a 16 here, 4 times 16 is 64, 10 times 1 is 10, and 5 times 16 is 80. When you add all this up, it comes out to very close to 250. I think it comes out to 249.5. I'm going to round it to 250. That's the number of grams in 1 mole. So if we were asked for the percent water, well, right here is the water. Here's my H2O. And this is 10 plus 80. This adds up to 90 grams of water. And in a total of 250 grams of my hydrated salt. And then multiply that times 100%. So we have 90 divided by 250. That's 0.36, which is equal to 36%. So that means that there are 36 grams of water in every 100 grams of hydrate. So if I knew that there were 30 grams of water in something, I could multiply that times 36 grams, or let's just say 36 water over 100 hydrate, and that would be equal to the amount of the hydrated salt, or 0.25 grams of monohydrate, higher salt plus water, times 36 water in every 100 hydrate. So that's how these work out. And again, 50% is the same as 0.5. So this is like saying 50 cents is equal to $0.50. Okay, this should give you a review of how to use percent composition.